Yeah, Kirtan, I'm audible.
Yes, sir.
All right. In the last class, what do you remember about the last class? What we had a discussion in the last class? I think I started with a chapter, magnetic effects of current. Okay. So thereon we discussed some basic things. Maybe till yeah, we discussed till the units of your magnetic field. Yeah, magnetic field strength basically. Till that particular point we discussed about, right? Okay. So now we discuss about a new term that is magnetic force on a monopole. Okay, placed in a magnetic. So, Kirtana, before going to this, can you just tell me one thing? I have a charge placed on here, okay, and in this particular region, basically there is an electric field in this region, maybe like this, okay, and I have kept my charge at this particular point. Can you tell me, and this electric field is constant throughout the line? Okay, can you tell me what is the force on this charge due to this particular electric field? Yeah, Kirtana, what will be the electric? What is the force on this particular charge due to this particular electric field? Kirtana, are you there?
Sir.
Yeah. What is the force on this charge, okay, due to this electric field? And what will be the direction also? Okay. And I'm taking the direction as this as okay, these as positive directions and the opposite one will be the negative. This is our direction coordinate. So please let me know what will be the force on this charge due to this electric field E.
Direction of electric.
How much?
The direction of electric field, sir. QE.
No, no, I'm not asking. I'm asking force on this charge. What is the force on this charge?
QE.
Q. Next. So similarly, we are going to talk about magnetic force on a monopole. Instead of this charge, I am going to place a monopole. You know, Kirtana, when we talk about a bar magnet, in general, we have two poles, right? A north, a south. And very well idea is there that you can't have monopole exist. But assuming if we have a monopole, okay, we are going to take a case where we have a monopole. So I'm going to say, let's take a case when I'm having a monopole. Let's talk about north as a monopole, right? And I am going to take B over here as a magnetic. Okay. So here we are going to calculate magnetic force on this monopole which is placed in magnetic field. Okay. Clear? So basically force, let's say due to this north pole, I'll just rewrite this thing back. This is a point which is a monopole N, basically north pole, and the magnetic strength, pole strength, basically the strength of this pole is positive. Okay. You know, for N we generally call this positive strength, and these N or basically positive side work as a positive charge. Okay. So what will be the force on this? You will say the force on this will be nothing but pole strength multiplied by B. Right? We have already discussed the same thing in the previous class itself. Okay.
Yes.
Now assume I have this kind of Here I had magnetic field, and here I had south pole. Who's this? Okay, so what is the magnetic field? You can simply say, sir, whatever force is nothing but pole strength. What is the pole strength? M. That magnetic field. So basically, direction of magnetic field is this way. So force will be this way. So this is the total force. Okay, that is what we are talking. Clear? Is it
Yes, sir.
clear? So basically, force. What is the force? Force is nothing but this pole divided multiplied by this. So if positive, then towards B, negative away from B. Is it clear? Away from. Basically, this is giving you direction. Okay. Opposite mhm, and yeah, that just force is my action. So this is basically the direction. You have to keep the sign convention. Now we can talk about magnetic magnetic force on a dipole, basically a bar magnet, right? So if you could remember, let's see, magnetic force. You don't have to. We will not going in derivation again because we have seen similar derivation current electricity itself. So magnetic force on bar magnet, okay? Placed in magnetic field, placed in uniform magnetic field, okay? Magnetic field. So Kirtana, if you could remember, what is bar magnet? Bar magnet is nothing but a magnet having dipole, right? So can I say it is basically acting as a dipole itself? And if I know all the properties of a dipole, how a dipole interact in your electric field, I can actually do the same thing. Instead of electric field, I'll be having this magnetic field B, okay, and this dipole we generally represent with Q. Here we represent the pole strength with F, right? So if I could remember all about these things, can I do the same thing over here also in case of bar magnet?
Yes, sir.
Okay, can you tell me what is the value of your what is the value of okay, yeah. Can you tell me if my magnetic field okay due to this I'm not having this force okay yeah. So assuming I have electric field just like in this direction. This is bar magnet I kept over here okay? And I have kept this into a magnetic field like this. So if you could remember, we have done the similar derivation in case of electric field. What was the topic? The topic is force on a dipole in constant electric field. Right? Here I am going to have a constant magnetic field. Clear? So here instead of this, I am just going to represent it with a this kind of point. Okay? This is your dipole. How we are going to represent it? You know very well that this particular point dipole goes from this B to this. So you can say this is north point and this is south point. Okay? This is how we are going to represent it. Okay. So Kitna, look, what happens here is I'm having a dipole. I kept a dipole. From here, I have this kind of dipole. Now you know we have all just studied that electric field on the dipole, magnetic force on the dipole. This is your north pole, okay, having M as a pole strength. This is your south pole having pole strength as a M, right? What we studied is force on your dipole. If it is positive, it is towards the magnetic field. If it is away, it is the away, right? Negative or away. So on this particular pole, we can. I'll just change the color to show this. For this dipole, the magnetic field or the magnetic force will be towards it because this is positive, right? So force FB. Here the force is opposite. Clear? And because of the whole thing, because what is the net force? If I ask you what is the net force, can you tell me the value of net force? Because look, if I ask you what is the net force, F net is nothing but force on positive, force on M negative, right? What is force on? Because the magnetic field is constant, you will say M times of B plus minus M times of B. So this results to negative. If the force is negative, if the net force is zero, F net is zero, the net acceleration will also be zero. But if you see carefully, what about the torque? If you see, what is the torque? Torque is nothing but F R cross F, right? This is R cross F. So if you talk about the torque is there. Why the torque is there? Because on this particular point, what is the distance? This is your radius vector. This is your distance vector from this particular point, from the center. This is your radius vector R. Okay, the distance is this R itself. The what is the total distance? If the length is L, this R is basically L by 2. So that's what we are keeping right now. And assume it to be 2L. It will be better for us to calculate. So if I ask you what is the value for this thing, you will say, sir, the R cross F comes out as F R times of sine theta. Okay, makes sense. What is the theta? Theta is the angle between R and F. Okay, R and F. This is it. Makes sense. Okay, this is the torque from one side, right? Is it the complete torque or is it the one-sided torque?
One side.
It's a both side, right? So you can simply say, what will be the complete torque we are going to get? We'll be having the same torque for this side also. So you can say, what is the torque in this particular piece? The torque will be torque from the upper and torque from the south. What is it? R cross F. Okay. So if you solve it out, again you are going to get F R sine theta. So what is the net? Torque net is nothing but summation about F R sine theta times of what is 2 F R sine theta? You can simply say this and this results to 2. If you call it as L. Yeah, because we are keeping different, right? So now you can say 2 times of F. This will result to how much? F L sine theta. What is force? Force on individual, or what is the force on individual? That is M times of B. L sine theta. Okay, makes sense. So if you see carefully, what is M into L? What is the dipole? What is the magnetic dipole moment? If you could remember, normal electric dipole moment looks like P is equals to what is the electric dipole moment? Q times of L, right? What's the distance between them? In a magnetic moment, what is it? Q times of M times of L, distance, right? So here you can say M and L nothing but capital M. This is dipole into V. Basically, it was MB sine theta in a normal way without this. So you can rewrite the same thing as MB of sine theta, M cross B of sine theta. This is the value of the net torque. This is the final torque on your bar magnet if you are going to keep that into the magnetic field. Just go through this once, and if you have any doubt, please let me
Load up. Load up.
know. All right, so we'll be going to discuss the next topic. But this. Okay, so we are done with this topic. It was just a very small topic. Okay. So far, we have discussed about the magnetic force on a bar magnet. Okay, if we have kept this in the uniform magnetic field. Okay, can you try once to calculate the same cos if you are kept that into the non-uniform magnetic field? Look here, now in this particular case, I have taken a constant magnetic field. Okay, I took a bar magnet and I tried to calculate force, net magnetic force on this bar magnet due to this magnetic field. Okay. Now, what I am asking you to calculate this in case of non-uniform magnetic field. Okay. Similar concepts we have already done in case of your electric field. When we were talking about the electric field or dipole in case of non-uniform electric field. So I can give you a timestamp of 3 minutes. You can derive this and let me know. Okay. The concept is similar. You can just try it once.
Okay, sir.
Yeah, so basically time is up. Have you got the solution for this one? Look,
No, sir.
look, look, I'll just give it once. Um, in case of dipole, when we studied about the dipole in electricity, we had P is equals to Q times of length, right? Here we have the similar concept, but I'll just write something. Electricity. Basically, we have done these things in electricity and here in magnetism. Here it is in magnetism. It will, this is magnetic moment, which is equals to pole strength multiplied by the length. Okay, this is one. Clear? I hope it's clear. The next part is force. Force on constant electric field. If you could remember, in case of force on a constant electric field, the net force was zero. Here also the same thing, right? Force on constant magnetic field. Magnetic field. What is the force? Zero. What about the torque? Torque in constant E. Yeah, right, E better. It was basically your P cross E. Here, what I'm going to get? This is the second. This is the third. Maybe. This is the so torque in constant E. Constant B basically. The representation of magnetic field strength is nothing but B vector. So that results you, yes, M cross. Any kind of doubt or a derivation required so far? Yes, sure. Yeah. Okay. Yeah, Kirtana. Yeah, okay. Okay, Kirtana, do you need any kind of derivation for all these parts? Any doubt you have? The things are very similar in case of electricity and this magnetism, whatever we are doing right now. So
Plus.
just the introduction portion. Okay. Yeah. So can you tell me what will be the potential energy of your bar magnet if I'm going to keep that into the electric field? Just think of dipole in electric field, potential energy there, and do the similar thing over here. Potential energy of bar magnet in electric field. What was that? U is equals to negative of m dot b cos theta. This was the formula. Make it yeah m dot b. This was the formula. In case of electric current electricity, you had the formula as potential energy of dipole in electric field. What was that? U is equals to minus m dot. Okay, this was the case in general. So if you don't have any kind of doubt for these particular point, I can move further.
No doubts.
No doubt. Okay, we can discuss about the force on non-uniform electric field. So if you see carefully, here I am getting the force as a constant, right? Assume that my electric field at this particular point is E x and here it is dx. No, what I can say. Okay. Assume that electric field is varying with E naught dx in this form. Okay. It has dependency on Ex. Basically, by the distance your electric field is varying. So in that case, what I can say here, what is the force? Fm is nothing but m times of sorry, it should be magnetic field, not electric field. I'm quite confused with these two terms. Yeah, magnetic. So MB. Okay, this is what you can do. For this particular point, you can call it as M minus. But if you see carefully what it is nothing but at x different and x plus bx. Because this MB was B is a function. Okay, you can't do like bx plus b dx. Okay, don't do this. So it's better you can rewrite the same thing as here value of p at distance x plus some extra value of bx. Okay, so we can call this as dv, a small extra dv. Okay, divided by here you have just bx. Okay, so what's the difference you are going to get net force because they are in opposite sense. So this will result you m times of d. This is the value of force you are going to get. Is it clear?
Yes, sir.
Net force. Now it actually depends how we are going to rewrite this net force because if the formula is like b is given as b naught times of x, maybe yeah, bx. So if I divide the whole thing by this dx, so what if I'm going to get is dv divided by dx is equals to something divided by dx over here. Okay, so what we are going to get dv as some b naught constant and the function of x divided by this dx. Something like this we are going to suppose to get. So you can actually substitute the whole this of the value over here and get the answer. Is it clear?
Yes.
Yeah, Kirtana, can you see the screen?
No, sir, it is blank.
It's blank. Right? I'll show. Okay, everything which I wrote in the previous session. Okay, Kirtana, look, whatever I wrote has been removed. So what we can do further? Look, I only discussed about magnetic dipole, right? Some forces on it. You can actually correlate that with the electric field. Here I was at the topic. What was the topic? Okay, look. So we have a magnetic dipole. Oh yeah, it's magnetic dipole. Force on bar magnet in non-uniform magnetic field. That's we can I can simply make it like this. You had a bar magnet which was represented in this format. Okay. Here the electric field, because this is not having M as a parity, so the force is going to be E. Okay, this is E. Makes sense. So actually, what you can simply do is make it here also. This will result to something E, some different value. This is at distance x. Okay, this was E, so it was an extra D. So what is net force? F net is nothing but M times of E dx, no, E plus E times of dx, the small difference, minus M times of E. Okay, if you resolve the whole thing, what you are going to get? M times of E times of dx. Now, what is this dx part? Any idea? This dx is basically the distance between these two points. Distance between these two points. So that is your F net is going to be like. More further. Okay. Yeah. So here now look, in general, we have two kind of equilibrium, okay? Stable or unstable. So assuming that because force torque on a dipole is nothing but P cross E magnetic. Here it should be your magnetic field. And U is equals to minus M dot P. Sorry, it should be capital M dot P and it should be capital M cross. So if I'm going to keep, assume this is your magnetic field, okay? And here I have a charge, basically a bar magnet, which is kept in a sense of, in this sense, okay, from here to here. This is a one configuration, and another case can be this. Here, your bar magnet is kept in this format. What about the magnetic moment? Assume this is the magnetic moment. Magnetic moment. Okay. Now, can you tell me which either of which case is equilibrium? Tell us the state of equilibrium. Mean to say whether it is stable, unstable, or whether it is in equilibrium or not. Okay, this is what you have to tell. Two figures are given to you, and this is the magnetic field direction. Identify out of these two whether they are in equilibrium, they are unstable, they are in unstable equilibrium. That is what you have to tell. Kirtana, can you give me the solution? Like, can you give me the answer for this one?
Both are stable.
Both are stables. Okay, now differentiate in between what kind of stability these are. Okay? What kind of stability are these? Because you know in equilibrium also we have multiple kind of equilibrium. Okay, so which equilibrium is it? Two equilibrium are there, stable and unstable. Okay, so which one is stable, which one is unstable? Yeah, Kirtan. Look, a very simple
Actually,
idea. If you see carefully in this case, just take the magnetic. The direction of this and this is this, right? So what is the potential energy you are going to get for this one? The potential energy suggests that, okay. So here this is the potential energy and you can, what's the formula for this? M dot B, right? So if you see, the both have a same direction. Both have same direction. So what will be the final answer? That will be minus M2. This is this. And in this case, it will be minus M dot B. Here, because M and B has a different direction, the product of them will be negative. So negative, negative become positive. Now tell me, you have two kind of potential energy. One is, assume that from here it is 0, here it is minus and maximum minus 1, maximum positive. So in which case do you think it is a state of equilibrium or unstable equilibrium, and which is the state of stable equilibrium?
positive is stable.
Positive and stable equilibrium. Okay. Let's not think in this way. Okay. Assume that, Kirtana, I'm giving you another example. Assume this is a bowl. Okay? You have two kind of bowl. Okay. Sorry, it should be like this. I have kept a coin at this particular point, and any ball I have kept. Okay. And another ball is over here. What do you think? Which is the state of stable equilibrium or which is the state of unstable equilibrium? What I am going to do is, you can do this by just give a small push to this ball. Okay. If it is able to if it is able to approach back to its original position, the previous position, then it is a state of stable equilibrium. Okay, otherwise it's not. So in which case do you think it's a stable equilibrium?
The coin and the balls.
Point in the ball. Okay, this is A and this is the B, right? Which case is stable or which case is unstable?
A is stable.
A is stable, right? Why? Because if you see, it has a minimum energy, right? If you look in that form of energy, at this particular point it is mgh and here it is 0. So because it is in the state of minimum energy, right? Here this point is mgh. If you give a small push, the ball will be reaching here. Okay, so from here it will have a lesser energy. It will try to approach down energy. Okay, it won't come back. In another way, if I have to look at this point, assume that what I'm doing is, I take it and I give a small deflection over. So a small deflection means to say it came like this and it come back like this. Okay, this is what I give a small push. So what do you think? Will it come back to the previous state or it will just turn back? I will say it is going to turn back because D is in this direction. Force at this point is going to be this. Force on this point is going to be this. So it will never be able to reach back to its position. Right? So can I say this is a case of unstable equilibrium?
Yes, sir.
Okay, because if you give a small deflection in case of equilibrium position and if it is not able to reach back to its previous position, then it's unstable. What about this? Let's say I gave a push and it can come to this position. Okay, here you can say this is not. Now here electric magnetic field force is this way, force is this way. So what will happen? It will come back to its position back. Okay, so this is the case of unstable. This is the case of stable equilibrium. Stable equilibrium. Okay. So potential energy is nothing but dF by dt. Understood? This is what your potential energy looks like. No, sorry, it is not. It is not. It is not. Force is nothing but minus du by dx. Okay, this is what the value is. So if the object has a minimum energy means to say it is in the stable equilibrium. Okay, more energy, it is able to move back. It will not be able to reach back to its position. So that is case of unstable equilibrium. Clear? I hope it's clear. So Kirtna, assume that I am having a uh, okay. Kirtna, just tell me, are you clear with your grade 11th concepts? Kirtna, are you clear with the
Not that
SHM
clear.
waves and all?
Not that clear.
Not that clear. You should be actually clear because the good problems are based on only 11 based topics. So I could skip this part because you are not clear with the previous concepts. But you should actually be clear with this, okay? Because in the this chapter and the upcoming chapters we are going to use it. Okay, so just a problem is given. This is your magnetic field B, and this is a dipole M. Okay? This is M, and moment of inertia about the center of mass is I. About the center of mass. Okay? So what I did, you have kept this at an angle theta. Okay, are you clear with what is inertia, moment of inertia? Kirtana, do you know what is monopole? Like what is the moment of inertia? Kirtana, please be fast.
Yes.
Okay, so you know moment of inertia, right? Okay, okay, I'll just give you one problem. I don't know whether you can try this or not. Okay, you can take it as a homework part. Look, what I did is here. I had this kind of configuration, a magnetic dipole, basically bar magnet, who's having a magnetic moment is like this, has a moment of inertia about the center I, and the angle is initial angle which I kept is theta negative. So because the force is in this way, so it will try to come back. When it goes to come back, what will happen actually? It will gain some velocity over here. Okay, it is going to gain some velocity. Due to that velocity, it will come back to this position, and after this, here it will lose its velocity, come back to it. So you have to tell me at which okay, what is the omega? Find you have to calculate. Find maximum omega. Okay, maximum omega. What is omega? Angular speed. Okay. Angle swept by something is not generally known as omega, angular speed. Okay, so you have to calculate the maximum frequency. Is it clear?
Yes.
Did you understand the problem, or you want any clarification for this? Because it's a homework for you. Okay,
Understood.
understood, right? This is given as inertia, so you have to use the concept of rotation mechanics a little bit. Okay, let's come back to another point. The last topic for this particular discussion. Look, in case of dipole, we generally calculated what is the electric field due to a dipole, right? Now we are going to calculate magnetic field due to bar magnet. Okay, magnetic field due to bar magnet. So I hope you should be clear with the concepts at any point. Okay? At any point, we are generally concerned with the. So assume this is your magnetic moment. and this is your dipole over here. This is a point M. Okay, M. So due to this M, what will be the dipole moment? Assuming this to be N. Okay. So due to this, magnetic field at this particular point will be nothing but this direction. Right? Radially outward. Clear?
Yes.
So the point is basically present over here. So the distance between this and this is point B, R. This is R. So magnetic field is in this direction. So you can say V is directly proportional to M. Right? What is this V? Magnetic field strength. Okay. And B is also inversely proportional to radius. Understood?
Yes.
Let's look about magnetic field due to we are calculating magnetic field due to bar magnetism. Sorry. What happens? Should not be like this. It is basically due to monopole. I have just kept a monopole n. So due to this, I'm going to calculate it. So you can say V is equals to K times of M divided by R square. This is your magnetic field value. Is it clear? What is the value of this K? This is basically a constant. So what is the value of this constant K? K is nothing but mu naught divided by 4 pi. Is it clear? In electricity, we had a constant K whose value was nothing but what was the value in that case? 1 by 4 pi epsilon naught. Okay. Here we have value as 1 by 4 pi as it is, but instead there here we had epsilon naught in the denominator. Here we have mu naught in the numerator. That is the only difference. Understood? Okay. So the B directly comes out as mu naught divided by 4 pi m divided by r. Understood? This is the value of magnetic field due to a monopole at some distance r. Clear?
Yes, sir.
Okay, and what's the value of this mu naught by 4 pi? The whole value of this mu naught for 4 pi is nothing but 10 to the power minus 7. And what about the unit? The unit for this is Tesla. Therefore, this is meter divided. It comes into the no, sorry. This is Tesla. This is what is the unit for this? Ampere per meter. So it will come into the division part. Ampere meter, and this is has m square. So what is the final unit? We can call it as sorry. What you can call this? You can actually call this as Newton per ampere. That the best value is Newton ampere speed. This is what you can call it. I'll give the reason also. Assume that what you are doing is multiply another m1, m2. What is this m1, m2? Another poles, okay? Two different poles are there. What is this? The whole thing is a value formula for the force. So can I say this whole thing is coming out as a force itself? So force is nothing but mu naught by 4 pi, okay, multiplied by m1, m2 divided by r square. If you see, the formula is very similar in case of electricity. Unit of this ampere and unit of this ampere divided by here 2 mr. Cancel, cancel, cancel. What is the unit of this whole thing? This is n divided by a square. From where this are getting here from here, this is what the unit is. Is it clear now?
Yes, sir.
Okay. Look, kid, now if you are clear with this concept, we can do everything by using this. Okay. Now, if I ask you, can you calculate the formula um, due to a bar magnet? Yes. Yeah. If I ask you now, can you calculate the magnetic field due to this bar magnet? Yes, you can actually do, because at any point you know what is the magnetic field due to this particular pole. Okay. You will get to from here also, and you can calculate it. Right? The similar case we used to do in case of your dipole. We had a two dipole. That was separated by some distance r, BB2L basically we used to say. So what was the electric field due to this dipole at this along the axis and the equatorial, right? If you could remember about these concepts,
Yes, sir.
right? Okay. Ketan, any doubt you have so far?
No, sir.
No doubt. Right? Nothing we have got. All right, Kirtana. So I'll end the session by this. In the next class, look, what we are going to discuss in the next class. Look, if I ask you, please keep me remember with this. We are going to calculate magnetic field due to a bath. Okay. And yes, I feel you are not clear with the previous concepts we have discussed so far. Okay. So please revise those. Otherwise, it won't make any sense to move further. Clear?
Okay, sir.
Yeah. So that's all for the today's class. Although we have not written a lot of things in the session, so still I'll share it with you. Goodbye, Kirtana. I'll end the session like this.